lecture on introduction to soft matter. And last time what we were discussing was the response of a classical elastic solid, and today what we want to look at is the response of a classical viscous fluid. And then obviously we are going to contrast the two, and you can understand that the viscoelastic response will be somewhere in between the two, right. So, we are today going to look at a classical viscous fluid. So, last time we had introduced the 6 different tests, right, and we had looked at details for that. So, the first test is again the stress control test and the release of stress, and then the third one is the strain control test. So, let us look at these 3 for a viscous fluid. So, once again what I have done is we have already in a sense conducted the experiment, and I have already drawn for you what the response should be. So, we will use that here. So, the first test is the stress control test, okay, as we had already discussed that. So, here what you are doing is you are applying. So, again what we are doing is we are going to apply a known amount of stress, and then we want to see what happens to the response of the material. Now, the linear viscous fluid, what did we learn about that in our undergraduate classes is that it cannot withstand shear stress. So, here when we say stress we are implying shear stress. So, it cannot withstand shear stress, which means that it will immediately start flowing, right. So, in a simplistic definition we know that a fluid cannot withstand shear stress, right. So, when we apply a known amount of stress, in this case the picture is quite different. You have a strain, but this strain starts increasing immediately because the material is flowing. So, imagine a parallel plate situation. So, if you want to imagine this, you can have a parallel plate situation where you are applying your sigma naught to this case. So, the fluid initially is at rest, but will immediately start to flow in response to this. So, your strain will keep on increasing till the duration of sigma naught, and if we neglect inertial effects, then this increase is linear. So, this is this diagram that has already been drawn for you. Please note that this neglects, okay, neglecting fluid inertia. So, in a sense at a very low Reynolds number condition. So, now interestingly, so your graph for epsilon is very different from that of a classical elastic solid. But if you look at epsilon naught, which is the strain is going to be constant. These are straight lines. So, the strain actually attains a constant value, and maybe I will write an epsilon naught dot here. So, the strain attains a constant value, and it remains at that value for as long as you provide the stress. And then the moment you release the stress, which is this test. So, this is the release of stress, the flow stops. So, the strain, which basically is a measure of flow, the strain also stops immediately. but your strain value is going to be. So, the fluid element, a fluid element, if it has moved from one point to another point due to your application of stress, it is not going to move back, right. So, it is just going to stay there the moment you release the stress, which means that the strain becomes constant in that case. So, we see that there is a small amount of difference with respect to that of a classical elastic solid, in that the stress and the strain diagrams seem to be different. But there is also a similarity in the sense that the stress and the strain rate, the strain rate response is very similar to the strain response in the elastic solid case. This already tells you that the constitutive relationship for a classical viscous fluid will have most likely the relationship, or will have the relationship between stress and strain rate in this case, where they will be linearly related. So, unlike the classical elastic solid where the strain and the stress are linearly related, here the stress and the strain rate are linearly related, right. Now, what happens to the application of a, so that we have completed the two tests, right. But what happens to the third case where we apply a known amount of strain, right. That was, if you remember, that was our third test, the strain control test. So, here earlier I had just written for you what the strain control test looks like for an elastic solid. So, I am just going to refer back to that for a minute. So, this is your classical, so this is your elastic response, where you had applied a known amount of strain and you had gotten a known amount of stress. So, basically even though you had flipped the experimental parameter, there was no change, perceptible change. But in this case, in the case of the classical viscous fluid, that is quite different. So, this is your classical viscous fluid. So, when a known amount of strain is applied, then your stress required to create that strain requires a instantaneously high stress. But to hold on to this epsilon or hold on to this strain, you do not require further stress. So, in your diagram, you now just have an instantaneously high stress response, but then it just goes back to 0. So, this is a very important difference between the two. Now, we had the difference between, so what is the effect of different strain histories, right. So, to go back to the strain histories, we have to go back to the previous diagram. So, now we have, this is your fourth test, where you have applied the strain through different the stress through different histories. So, when you reach sigma naught through different ones, you are going to in the strain rate diagram, you are also going to reach the same strain rate at epsilon naught, and let us mark this as T dash. So, what has happened is this is okay, just complete this marking T dash. So, sigma naught you are reaching through different stress histories, and 3 possible ones are shown here A, B and C. So, in that case what will happen is the strain rate will also reach the previous value through different strain histories. But how it reaches the strain histories will remain will be different, but it will still reach the same value at end of T dash. So, when you look at the strain diagram, that is when you start seeing that the 3 cases are separate in terms of the strain. So, they have reached very different values in this graph, and in the beginning of course, this is just an idealization that your the strain rate here remains constant. So, at the end of the experiment, when the experiment has ended at T end, you end up with different displacements. But here your epsilon naught has again instantaneously decreased. Instantaneously decreases to 0 when stress is released. So, since they have reached different displacements, the fluid is going to continue remaining in that in the state of that displacement forever till you again apply some known force. So, we have been able to discuss the 4 different problems, the 4 different cases. Right. So, now we have 2 more left, which are the energy dissipated in the system and the effect of sinusoidal oscillations. So, when it comes to energy dissipated in the system, you now see that there is a very critical difference between the elastic solid and the viscous fluid, and that is that the displacement that you have provided to the system is not recoverable. So, the displacement is not recoverable, then the energy that you put into the system is also not recoverable, right. So, let us write that down. So, energy dissipation, just a second. Energy dissipation. So, displacement my spelling is wrong. So, displacement suffered by the system is not recoverable. And hence, the energy input or the input energy is also not recoverable. So, if the energy is not recoverable, what has happened to it? It has been lost through dissipation. So, energy has actually been lost through dissipation. So, see there is a very interesting difference between a classical elastic solid and a classical viscous fluid in the energy sense. They are the extreme opposites. While one stores, the ideal classical elastic solid will store energy for you for an infinite amount of time, the classical viscous fluid will lose all the energy that you have put in, all of it is dissipated. So, now since you have been doing all these different experiments, you have realized that the relationship between the, in the case of the classical viscous fluid, the relationship, constitutive relationship will be between the stress and the strain rate, right. So, your stress in this case, when you do all the different experiments, what you find is where mu is a material property. Obviously, it is viscosity here, the shear viscosity. Which, now that you have determined this, it brings us back to the last problem, which is sinusoidal of the sinusoidal oscillations. So, in sinusoidal oscillations, your input is epsilon equal to epsilon naught sine of omega t. Let us say, then your sigma t is mu naught or mu sorry mu epsilon naught omega sine of omega t plus pi by 2. So, I have just used this relationship to get this relationship between the sinusoidal oscillations. And you see now one more interesting difference between that of a classical elastic solid and a viscous fluid, right, that in that case the two were exactly in phase, here they are exactly out of pi by 2 phase. Okay. So, note pi by 2 phase difference. Also note that omega now appears in the relationship. So, if you take maybe for completeness I will just write this as epsilon t, just a second. So, if you take the ratio of epsilon t and sigma t, then there is an omega term that is going to be there. So, it is dependent upon the frequency of oscillations, right. So, this is another important difference between the two. So, now we have completed 6 tests. We are ready to compare our results for the classical elastic solid versus a classical viscous fluid. We have seen these two diagrams earlier. So, this is the response of stress for a classical elastic solid, and you can compare that with that of a classical viscous fluid. I have deliberately left one column empty, which is for a viscoelastic fluid or a viscoelastic material. So, you can imagine what the viscoelastic material probably would be. It would be somewhere in between the two responses, right. Another part was, sorry, I am going to come back to that. Another was the step strain test, where in a classical elastic solid what you had is you applied a known amount of strain, and the system registered a known amount of stress, a certain amount of stress, and that value of stress was being kept at that value for a long time. In a classical viscous fluid, the behavior is quite different than that. So, the viscoelastic material response will probably be somewhere in between these two. So, now that we have done that, or we have compared these two cases, we are ready to understand the response of a viscoelastic material. Okay. So, response of viscoelastic material. So, what we are going to do is going to do the first test where we are going to apply a known amount of. So, you are now back in the laboratory, you are going to apply a known amount of strain, and just for quick recap, you are doing, and I mean doing, the reason I am going to do the recap is just because I am going to show you how. So, when you are measuring the material response for your classical elastic solid, what you found is, you found that when you gave a sigma naught, you registered a value of strain. In this case, for that of a classical fluid, this kept on increasing. So, how will your viscoelastic response look like? Okay. So, I am just going to write down what I have done here, just a second. So, this is your experimental, so rather the stress control test. When you were working with a classical elastic solid, you got this response. This is the response for a classical viscous fluid, and here you are trying to understand the response of a generic viscoelastic material. Just for completeness, I will also say epsilon t, this is also epsilon t. Okay. So, you will probably get a response like this. Where this response is composed of two parts. One is an instantaneous increase in strain, classical elastic solid, and then there is a constantly increasing part, which is that there is a increase in strain with time, just like your fluid. So, this is your straining with time, or the flow basically, which you also call creep, the creep response. And what do you think will happen when you release the stress? So, I am just going to copy this previous. So, now I am just going to complete this diagram, which was so it will end at some point. Rather, this is too much space. So, in this case you are going, this is your epsilon t, okay. The three cases. So, again, so we have already drawn the first part, right, which is, which looks like this. But what happens when the stress is released? So, let us call this T end. So, let us say this is the T end here, and what I am going to do is I am going to leave you with this for the next class. Okay. So, I want you to try and figure out what this response is going to be, and in the next class we are going to see what it really is. So, today what we did is continuing on those 6 different experimental methods to evaluate a continuum material. We looked at the classical viscous fluid, and we just got started with the response of a classical or rather sorry, a generic viscoelastic material. Okay. And in the next class we will continue this.